Okay, so what we looked at so far with the VPN configuration is just creating basic virtual routing and forwarding instances on the routers, applying them to the interfaces, and then running VRF-aware protocols on those interfaces. Okay, so all the configuration we've done so far is considered VRF Lite because we are doing it between directly connected neighbors, and we are not involving MPLS label switching at all. Okay, so MPLS was not running on the interfaces between router 2 and router 4 that were running those protocols. Now, technically, you could build an entire service provider network using VRF Lite and separate the customer routing information using the VRFs. Now, the disadvantage of doing this is that everyone in the transit path would have to be carrying every single route inside all of the VRFs. And I mentioned briefly yesterday, one of the main advantages of MPLS is that it gives you this quote-unquote BGP-free core type logic, where the devices in the transit path, they only need to know about the internal routes inside of the service provider. They do not need to know the global internet routing table, and they do not need to know all of the routes that are coming from the customers. MPLS VPNs is going to take this principle of how the VRF routing worked and allow us to do it between devices that are not directly connected. And this is going to be accomplished through multi-protocol BGP. Okay, now we saw briefly when we looked at the VRF-aware BGP table, the way that it was keeping track of an individual prefix is based on that route distinguisher. Okay, the route distinguisher, let's see, I think I have a slide on it here. The route distinguisher is an 8-byte value that is typically unique on a per VPN or per VPN site basis. In order for the VPNs to exchange information, they technically do not have to have the same route distinguisher. The route distinguisher is used just to make the individual route unique. Okay, so the route distinguisher should be globally significant throughout the entire MPLS cloud. Then you add that to the IP version 4 prefix, and it's going to make that globally significant. Okay, so if we have the same IP version 4 prefix, let's say we have the network 10.0.0.0/8. Okay, we can have this inside 10 different VPNs as long as the route distinguisher for those VPNs is different. Okay, so as long as the route distinguisher is different, then it's going to keep the individual prefix different. And now there's two different formats that we can put the route distinguisher in. We can put the BGP AS plus a number afterwards, or you can use an IP address and then the number afterwards. It's an extended community, so it uses the BGP extended community format. So either we can do, typically we're going to use our autonomous system number plus a locally significant number, or we can use the router ID of the provider edge router and then some locally significant number. Okay, so the advantage of using the second format with the IP address, we can see not only that the prefix is unique, but what specific provider edge router is it coming from. So for example, let's say that the router ID of router 1 is 150.1.1.1. We could say the route distinguisher is 150.1.1.1:1. So when we look at that prefix anywhere in the MPLS network, we know that, oh, this was originated by router 1 because we can see its router ID is embedded inside the route distinguisher. Okay, so the route distinguisher is used just to keep the prefix unique. Okay, so the first step in MPLS VPNs is that we have this unique prefix that's based on the route distinguisher. Okay, the next step is going to be exchanging MPLS tags or MPLS labels inside the transit network and using VPN-based labels to determine where a final destination is inside the MPLS network. And one of the advantages we talked about in MPLS yesterday is that there's effectively an unlimited number of MPLS labels that you can add onto a packet. Okay, at a certain point, it's not going to become feasible because you're going to have such a small payload that is going to have to be fragmented. But typically what you'll see is that in a VPN environment, you'll have maybe 2, 3, maybe 4 labels maximum. So if you're doing MPLS VPNs and then you're doing traffic engineering, maybe you're doing carrier supporting carrier at the same time, your label stack will be maybe 3 or 4 labels deep. Okay, but what we're going to see here is that there's going to be 2 labels that we are dealing with. We're going to be dealing with an IGP label, which is going to be our transport label, and we're going to be dealing with a label that is derived from BGP, which is going to be our VPN label. Okay, now the logic that's going to happen, we have the same type of setup we did yesterday, where traffic is going from router 7, and in this case it's going to backbone 1. Now the routing advertisement, we have a network X that is being advertised via backbone 1. So either we have some type of IGP that's running between these neighbors, or we have BGP running between the neighbors. Okay, the next step, we have the label distribution inside the service provider network. Okay, router 6 is telling router 5, in order to get to me, use implicit null. I want you to perform the PHP operation, the penultimate hop popping operation. So when you send me a labeled, when you send me an MPLS packet, I want you to send it not as a labeled packet, but just as a regular IP version 4 prefix, because I am connected to the final destination. A router 5 then says to router 1, if you're getting to router 6, you're going to use label L1. Router 1 says to router 3, if you're going to get to router 6, you're going to use label L2. Okay, so first step, we have our basic label distribution inside the service provider network. Okay, now we are going to build a VPN label on top of that. So backbone 1 is advertising this network X to router 6. Okay, we could be learning it via IGP, we could be learning it via BGP, we could be learning it statically. Okay, so any of those VRF-aware protocols that we saw, we could be running those between router 6 and backbone 1. Okay, so router 6 knows about the advertisement. The next step, it's going to turn around and advertise this into BGP over to router 3, who is the other provider edge router. Okay, so we have a BGP session that is established between router 3 and router 6. In this case, router 1 and 5, they are not running BGP. They're only running our IGP, and they are running MPLS. Okay, so router 6 says to router 3, if you want to reach that network X, you're going to use BGP. I am the next hop for that destination. Additionally, when you send me the traffic for that, I want you to use a VPN label V1. Okay, then router 3 is going to take this and advertise it to the customer edge, which is router 7, which could be either through IGP, BGP, or router 7 could just be doing a default route or a static route. Okay, but the key here we're going to see with MPLS is this exchange between router 3 and 6 advertising in addition to the regular label that was advertised through LDP or TDP. We're going to have a VPN label that is distributed via multi-protocol BGP. Okay, now when we go to send traffic through the network, what we're going to see is that router 7 sends an IP version 4 packet over to router 3. Okay, router 3 says, in order to get to destination X, I'm going to use router 6. That is my BGP next hop. When we do route recursion for the BGP next hop, we find that it points out an interface that is running MPLS. So we now know that this packet is going to be MPLS encapsulated when it goes out to router 1. Additionally, inside the BGP lookup, it sees that there is an MPLS tag associated with the BGP route, with the final destination, which is network X. So what router 3 does is it imposes the VPN label that was learned through router 6, and then it imposes the IGP label, or the transport label, that was learned from router 1. Okay, so it's taking the IPv4 packet, it's imposing the BGP label, so the BGP label from router 6, then it is imposing the IGP label, which was learned from router 1. Now, when router 1 receives the MPLS label packet, it is only looking at the topmost label in the stack. So it's saying, I received label L2. Now, if we look at our previous IGP label distribution, router 1 said that if I receive label L2 in from router 3, I'm going to swap it with label L1 and send it out to router 5. So if label L2 comes in, we're swapping it with L1 and we're sending it out to router 5. Now, once router 5 receives the label, it's saying, I received a label packet from router 1. It has label L1. Based on my label forwarding information base, I know this needs to go out to router 6, and I'm going to perform the penultimate hopping process. So I'm going to remove label L1 and send it out to router 6. When router 6 receives it, it sees that it has a VPN label that was imposed by router 3. The final destination is X, and it knows that based on the underlying VPN label that was inside the label stack. Okay, so when we take a look at this on the command line, we'll see exactly the difference between the VPN label and the IGP label. Okay, so what's going to happen in the traffic flow again? Router 7 sends it as a regular IP version 4 packet. Router 3 says that it's destined for X. X is learned via BGP. Okay, X is via BGP through router 6's loopback. I have a label switch path towards router 6's loopback. Additionally, I have a VPN label that was learned from router 6 for destination X. So I'm going to impose the VPN label, V1, then impose the transport label, telling everyone in the transit path that this packet is going towards router 6. So router 1 and router 5, they do not need to know that the final destination is X. The only thing they know is that it is going towards router 6. Once the packet gets to router 6, it knows what the final destination is. And the reason why is because router 6 has that VRF table installed locally. Okay, so the key concept here is that in addition to our regular IGP label advertisement inside the service provider network, we're going to be running multi-protocol BGP between the provider edge routers. Okay, we'll look at some more advanced design later where we can do VPN route reflection. We could also do this in confederation, but it's the process of enabling this VPN v4 address family between the neighbors that is going to allow us to advertise an MPLS label along with the VPN tagged route. Okay, so two different things are happening through the VPN v4 advertisement. We have the route distinguisher plus the route. This makes it unique. Okay, this is what is called a VPN v4 route. Okay, it's simply the route distinguisher prepended on to the IP version 4 address, IP version 4 destination. Okay, then we advertise the label, the VPN label. This is going to allow us to figure out what is the final destination for the packet based on the MPLS switching. Okay, so what we're going to do here, let's go ahead and set up the situation like we had yesterday with basic MPLS transport between the neighbors, but now we're going to run a VRF instance on the provider edge. So we're going to run a VRF instance on router 3 and on router 6, and they are going to be running VRF aware protocols with the customer edge. Okay, then between router 6 and router 3, we're going to be running multi-protocol BGP. Okay, so first off, we're going to configure VPN-A on router 3 and configure VPN-A on router 6. Okay, router 7 is going to participate in VPN-A, and backbone 1 is also going to participate in VPN-A. Okay, so first off, let's test basic connectivity. Let's go over to and we should have connectivity to router 7, 37.7, okay, which we do. We should have connectivity to router 1. From 1, we should be able to reach router 5. From 5, we should be able to reach 6. And then from 6, we should be able to reach backbone 1. Okay, so in this case, router 7 and backbone 1, they are going to be our customer edge routers. So we're going to receive routing information from them, pass it between router 3 and router 6 using multi-protocol BGP, and it's going to go back into the whatever the PECE protocol is running between the provider edge, or the provider edge and the customer edge. In this case, first we'll start by running RIP version 2 between the neighbors, then we'll go ahead and run some additional PECE protocols. Okay, so our first step here, we need to make sure that the MPLS network is built. So we're going to say show MPLS LDP, or let's say show MPLS interface. Let's see what interfaces we're running MPLS on. Okay, we have it on gigabit 00, we're running TDP. Okay, whether we are running tag distribution protocol or label distribution protocol, the operation is going to be exactly the same. Okay, the only difference is that they're using different protocol mechanisms to exchange the labels. But the label exchange is locally significant on a hop-by-hop basis. So we can run TDP in some portions of the network and LDP in other portions of the network, okay, as long as we are adjacent between the directly connected neighbors. Okay, so on router 6, let's make sure that we're adjacent with router 5. We'll say show MPLS LDP neighbors. Okay, we see we do have the connection to router 5. Router 5 should see adjacency with router 1 and router 6. Okay, which it does. Router 1 should see adjacency with router 5 and router 3. Okay, router 3 and router 5, we have LDP adjacency. And router 3 should see adjacency with router 1. Okay, next thing we're going to look at is the MPLS forwarding table built for our interior gateway routing. We need to make sure that we have transport between the provider edge routers. Additionally, we need to make sure not only do we have IGP transport, but is it an end-to-end label switch path? If there's a problem in the label switch path, if the PHP process, for example, is happening on the wrong router, we're going to have problems with the VPN transit. So when you're building the network, you need to make sure you're testing this stuff in a structured fashion. So first off, do I have basic layer 2 connectivity between the devices? Do I have IGP reachability? Once I have my IGP network built, I can put MPLS on top of it. Once I have my end-to-end label switch path with MPLS, then I can think about doing advanced configurations like MPLS VPNs or traffic engineering. Okay, so we're going to look at show MPLS forwarding table. Okay, show MPLS forwarding table, and we can see that we do have a label switch path over to router 6. Okay, so on router 3, let's go ahead and ping 150.1.6.6, and we're going to source this packet from our own loopback, because when we build the BGP session, this is what we're going to be sourcing it from. It's going to be coming from router 3's loopback going to router 6's loopback. Okay, we see we do have connectivity. Based on this, the label switch path, we should see this end-to-end. So what we really need to do is either we can debug to see if this is actually an MPLS path, or we can look on a hop-by-hop basis. On router 1, we'll say show MPLS forwarding table, and we'll include either 150.1.6.6/32 or 150.1.3.3. Okay, we don't really care about a label switch path to the other destinations in the network. The only one that we need right now, is the label switch path between router 3 and router 6's loopback. Okay, so we can see we do have a label for router 6. It says it's going out to router 5. The label for router 3 says we're going to perform PHP. We're going to pop the label, and we're going to send it out to router 3. Okay, this is the correct operation because we are directly connected to router 3 in this case. Okay, then we go to our next hop, which is router 5, and we should look at the same thing. As we're going to router 6, we're going to perform PHP because we are directly connected to router 6, and we have a label switch path that is going to router 3. Okay, so we can see the LSP is built end-to-end. Without this label switch path, when VPN traffic tries to transit the network, it's going to be black holed on either router 1 or router 5 because they do not have the routes to the final destination. Okay, so router 1 and router 5, they're not going to run BGP. They're not going to know about any routes that are learned from router 7. They're not going to know about any routes that are learned from backbone 1. They are depending on this label switch path between router 6 and router 3 in order to provide transport between the neighbors. Okay, so that is our first step. Okay, now we can go ahead. We're going to configure the VRFs on router 3 and router 6, and we're going to exchange routing information with the customers. Okay, so on router 6, we'll say IPVRF. We'll say this is VPN-A. Okay, VPN-A is going to be the name of the VRF. We'll say the route distinguisher, we'll use our loopback here. We'll say this route is coming from 150.1.6.6:1. Okay, so we could say for every VPN, we'll use the same number here, and we'll use the router ID of the originating router. Okay, this would be one system that we could keep track of the individual VPN routes. Or we could say use the BGP autonomous system number. We'll say our autonomous system is 100, and then this is the first VPN inside our network. Okay, so the route distinguisher is going to be based on whatever administrative policy that the service provider wants to set up, as long as at least on a per VPN basis it is unique. Okay, ideally, we would have it unique per provider edge, because then it's going to make troubleshooting a little bit easier. Okay, but depending on how many provider edge routers there are, it may be too big for the service provider to keep track. Okay, so in the case of the lab exam, either they're going to tell us what to use, or we should come up with our own scheme to figure out where the prefixes are coming from. If you come up with your own scheme, then I would recommend to do this, using the router ID. Because when we look throughout the network, we're going to see anything that is tagged with 150.1.6.6, we know that originated from router 6. Okay, the next step, we're going to go ahead and apply the VRF to the interface. Okay, so we'll show run interface serial 0/0/0. So on this interface, we'll say IPVRF VPN, or IPVRF forwarding VPN-A. Okay, that's going to remove the IP address from the interface. So we need to go ahead and apply it back. Okay, now we'll test connectivity again, but we're going to ping inside VRF VPN-A. So we'll say ping VRF VPN-A 54.1.1.254. That's the destination. Okay, we see we have connectivity. Okay, now we'll go ahead and run a routing protocol instance inside VPN-A. So we'll say in this case we're going to run RIP, and we're going to run a RIP instance for VRF VPN-A. We'll say this is RIP version 2, no auto summary. The network we want to run it on is the 54 network. Okay, so if we look at the routing table on router 6 here, if we do show IP route, we can see we have the IS to IS learn information. This is the internal global routing table. So this is the table that the MPLS tags are built off of to provide transport within the service provider network. So router 1 and router 5, this is the table that they should see. They should see this IS to IS learn information. Okay, now we have an additional routing table that is going to be for VRF VPN-A. We should see RIP routes that are coming from backbone 1 here. Okay, which we do. So inside this particular VRF instance, let's take a look back at the topology here. Okay, so the diagram here shows that we're running BGP. Once we get the basic MPLS VPN working, we'll go ahead and run the variety of PE to CE protocols here. Okay, but in this case, we're running just basic RIP version 2 between router 6 and backbone 1, and we're going to run RIP version 2 between router 3 and router 7. Okay, so we have the VRF routing working on router 6. Now, if we say ping VRF VPN-A, we'll try ping and we'll say 212.18.0.1. That's one of the interfaces that backbone 1 has connected. Okay, so we see we do have connectivity to this. Okay, let's say also on router 6, let's create a new loopback interface, and we're going to go ahead and advertise this into the VRF as well. So we'll say this is interface loopback 1. Interface loopback 1. We'll say our IP address is 10.1.6.6/32. Okay, this is going to be in VRF VPN-A. IP VRF forwarding VPN-A. Okay, under the RIP process, address family IPv4 VRF VPN-A, we'll also put a network statement for this 10 network, a network 10. So this advertisement should go out to backbone 1, and if we say now ping VRF VPN-A, we're going to ping, we'll ping that same route, but we're going to source our traffic from 10.1.6.6. And we see it's successful. So what this is showing us here is that not only are we learning the RIP routes from backbone 1, they are learning routes from us as well. We're sending them an update about that 10.1.6.6 network, that host route. Okay, now let's go ahead on router 3. We're going to do the same configuration. Okay, first step, we're going to create the VRF, IP VRF VPN-A. We'll say for the route distinguisher, we're going to use our loopback address. And we'll say this is VPN instance 1 inside our SP network. It will have a new loopback 1, that is in IPVRF forwarding VPN-A. Its IP address will be 10.1.3.3/24 or /32. Okay, then attached to router 7, we're also going to run the VRF. So we'll say IPVRF forwarding VPN-A, IP address or on the Ethernet. Okay, then we'll reapply the IP address. Okay, next step, we'll go ahead and run the RIP process, the VRF RIP process on router 3. Then we'll go ahead and configure a regular RIP process on router 7. Okay, so we'll say router RIP here, address family IPv4 VRF VPN-A, no auto summary, version 2, network 10.0.0.0. Now on the customer edge, which is router 7, we're just going to configure a regular RIP process. Now if this PE to CE routing is working correctly, we should be able to see on router 7 we show IP route RIP, we should be getting that loopback from router 3, which we are. Okay, so if we ping 10.133, we'll source this from our own loopback, which is 10.177. Okay, so we have connectivity between the provider edge and the customer edge. Okay, now what we're going to do is run BGP. We're going to run multi-protocol BGP between router 6 and router 3 to exchange these individual updates. So the RIP updates that are coming from router 7, router 3 is going to take them and redistribute them into BGP. Okay, likewise, when router 6 is receiving an update from backbone 1, it's going to redistribute that into BGP. Okay, unless we are running BGP as the PE to CE protocol, it is implied that we need to perform redistribution. Okay, so if we're running OSPF on the provider edge, we would need to take OSPF and redistribute into BGP in order for the rest of the provider networks, or the provider routers, to get that information in BGP. Okay, so on router 3, we're going to run BGP AS100. Okay, we are going to peer with router 6. We're going to source our updates from our loopback. Okay, now, whenever we initialize the BGP process, let's go ahead and do this on router 6 first. So router BGP 100. Neighbor 150.1.3.3, remote AS100. Update source is loopback 0. Whenever we configure basic BGP, what we're going to see here is that we are enabling the IP version 4 unicast address family. Okay, IP version 4 unicast is going to be default whenever you run BGP. So if you want to exchange regular IPv4 routes, that's going to be automatic when you configure a BGP peering. Okay, that's what everybody, at least up until this point, we should be comfortable with exchanging those IPv4 updates. Okay, so we just configure the neighbors, we configure network statements under BGP, or configure redistribution into BGP. That's going to get our IPv4 updates in there. Now, in this case, we technically don't need to run IPv4 unicast between the neighbors, because we're not going to be advertising regular IPv4 routes. Okay, we have our IGP that is advertising the routes within our network. We don't have a need for unicast IPv4 BGP. So what we can do here under the BGP process, we can say no BGP default IPv4 unicast, which means that when you configure a neighbor statement, you will not automatically activate the IP version 4 address family. Okay, if we look at the show IP BGP neighbor output, what we'll see here is we have an adjacency with router 3. It says the neighbor capabilities. We have advertised route refresh, and we have advertised IPv4 address family. Okay, so by default, they're automatically going to advertise that they support IP version 4 unicast routes. So we can either say in global BGP process, we can say no BGP default IPv4 unicast, or we could go under the address family. We could say address family IPv4 unicast, and for this specific neighbor, 150.1.3.3, we do not want to activate the negotiation of the IPv4 address family. If you're going to do the no BGP default IPv4 unicast, keep in mind that the order of operations is going to be important here. If you configure the neighbor first, like we did, this BGP default IPv4 unicast, it's only going to apply to subsequent neighbor negotiations. Okay, so if you want to manually specify exactly what address families you are advertising, you would want to specify this first. So you would initialize BGP, you would say no BGP default IPv4 unicast, and if we wanted to exchange IPv4 unicast, we'd say for this specific address family, I want to negotiate with this neighbor. Okay, that's what the activate command is doing. So we're saying with router 3, we've already established our TCP neighbor relationship. Okay, the neighbor relationship is independent of this. Once the neighbor relationship is established, then we negotiate what address families we're going to support. Okay, the neighbor 150.1.3.3 activate in there is going to be in there under IPv4 unicast by default. Now, what we do want to do instead here is we want to run a different address family. We want to support the VPN v4 address family. Okay, for the current releases that we are working with, we only have the unicast option. In the newest 12.0s versions, there is an option for VPN v4 multicast, which is used for inter-AS MPLS VPN multicast. Okay, but for our purposes, when we're dealing with VPN v4, it's just going to be for IP version 4 unicast. Okay, so now we're going to say that we want to negotiate this address family with router 3. So we're going to say neighbor 150.1.3.3 activate. Okay, on router 3, we're going to do the same thing back to router 6. We'll say address family VPN v4 unicast. For this neighbor, see, we can see we're getting an error message here. It says we have an unsupported capability with this neighbor. So router 6 is trying to negotiate VPN v4. We didn't put this address family, or we didn't put the activate command yet. Okay, so they're complaining that they do not support the same capabilities they're trying to advertise. So under address family VPN v4, we're going to activate this neighbor. Now, if we look at the show IP-BGP summary output, we can see that we are trying to establish an adjacency with router 6 for IP version 4 unicast. It says that the BGP neighbor is up. If we look at the show IP-BGP summary output, we see that we have not negotiated the IP version 4 address family. So even though it's telling us that the neighbor is up, but this default negotiation, which is normally there, IP version 4 unicast, it did not happen. So we cannot advertise IPv4 routes. We cannot receive IPv4 routes from them. What we have negotiated, however, is VPN v4 connectivity. So if we say show IP-BGP VPN v4, we want this to correspond to all VPN connections we have. We see that we have established negotiation with router 6. Okay, we're not learning any updates from them yet. Okay, this is because we did not redistribute between the IGP and the BGP processes. Okay, so the next step that we're going to do is under the BGP process, we're going to create a specific VRF-aware instance. We're going to say that we have a specific IPv4 VRF instance for VPN-A. We want to redistribute any RIP updates that are in the, or any RIP routes that are in the VPN-A table into BGP. Likewise, with BGP, or in the RIP process, we want to redistribute BGP. Redistribute BGP 100 metric 1. Okay, so we're doing mutual redistribution between BGP and IGP now. Okay, we're going to do the same thing here on router 6. So under the BGP process, we'll say address family IPv4 for this specific VRF. Our VRF's name is VPN-A. We're going to redistribute RIP routes into BGP. Then under the RIP process for this VPN, we're going to redistribute the BGP routes. Okay, but this is specifically saying only redistribute BGP routes that are in the VRF VPN-A table of BGP. So it's not going to be everything in BGP, it's just going to be stuff that is learned from this particular address family. for that particular VPN. Okay, now we can verify this locally if we say show IP BGP VPN v4 all. Okay, so we can see these updates. These are coming from Backbone 1, and we are redistributing them into the BGP process. Okay, so we can see they're appearing in the BGP table. Okay, we don't yet see the updates coming from router 3, but we do see the local routes coming from our IGP table, our IGP VRF table, going into BGP. If we go to router 3 and look, show IP BGP VPN v4 all, we see the same output. Okay, we see this is the route that is learned from router 7. We've redistributed into BGP. Okay, now at this point, we're doing the redistribution, but as of yet, router 3 and router 6, they are not exchanging the routes that are in this particular VRF. Okay, this is going to be based on an additional attribute that we need to define inside the VRF, which is known as the route target. Okay, now we looked at so far the route distinguisher in BGP, and what this was used for is to make the unicast route, the IPv4 unicast route, globally unique throughout the VPN BGP advertisements. Okay, so we took our route distinguisher, we prepended it onto the IP version 4 route. That is making it globally significant. Okay, this is globally significant because the route distinguisher is globally significant. Then we don't care if the IP version 4 route is overlapping. Okay, so we could have 10 different customers using the same RFC 1918 address space. That's not going to be any problem because the route distinguisher is unique. Okay, what we additionally need to do here is tell the routers what routes they want to take from BGP and advertise into the VRF tables. Okay, the route distinguisher does not control how routes are exchanged inside the VRF processes. The route distinguisher is used just to make the route unique. Okay, the additional attribute we're using is called the route target. Okay, the route target is going to control what enters the VRF table from BGP and what is exiting the VRF table and going into BGP. Okay, so BGP to the VRF and from the VRF into BGP. Okay, this is going to be based on an import route target and an export route target. The export route target says what routes are going to go from the VRF into BGP. So from the perspective of BGP, we are exporting them into BGP. The import route target controls what is taken from BGP and imported into the VRF. Okay, so export is going from the VRF to BGP. Import is going from BGP into the VRF. Okay, now this route target is going to give us some very granular control over what routes can either enter or exit the VRF. Okay, we're going to look at this through a couple different VPNs. We're going to look at things like central services and management VPNs. We can tag specific prefixes with different route targets to control what VPN sites they're advertised to. Okay, the route target uses the same format as the route distinguisher. It's a BGP extended community attribute, and it's using either the autonomous system number followed by a colon and then a number, or an IP address and then a number afterwards. Okay, so unlike the route distinguisher, which is unique for the prefix, this is controlling which prefixes can actually go in or out of the VRF tables. Okay, now one of the things that is going to be important here related to the route target, BGP VPN v4 has an optimization that says I am only going to accept routes through VPN v4 which I have matching VRFs that support that route target. Okay, this is an optimization of how many routes you are going to install in your BGP table. Okay, so let's say we have 10 customers that have 1,000 routes each. Okay, if every router, if all of those 10 routers are exchanging BGP, each of them would have to have the routes in each table. They would have to have 10,000 VPN routes. Now let's say a situation, let me bring up a whiteboard here. Okay, let's say that these three routers, these are provider edge routers, and they are running BGP with each other. Okay, so we have a full mesh of VPN v4 BGP sessions. Okay, so we have router 1, router 2, and router 3. Okay, on router 1, we have two different VPNs. We have VPN A and we have VPN B. On router 2, we have VPN A and we have VPN C. On router 3, we have VPN B and we have VPN C. Okay, so three different VPNs we're exchanging between these neighbors. Now, what the default policy is going to be in BGP is that router 2, when it is receiving an update from router 1, is going to say, do not send me routes that are from the VPN B. Okay, I do not have VPN B locally assigned, do not send me those routes. Okay, likewise from router 3. As router 2 is receiving an update from router 3, it's going to say, do not send me routes from VPN B. I don't have any local interfaces in VPN B, so there's no reason that I need to take up extra space in my table by installing those routes. Okay, with the BGP capability of route refresh, if VPN B is added in the future to router 2, it can request a triggered update from its neighbors. It can say to router 1, okay, now I want you to send me VPN B updates. And from router 3, now I want you to send me VPN B updates. Okay, but the default behavior that we're going to see is that the routers automatically filter out routes based on the route targets. So if there's a route target 10 somewhere in the network, I am not going to accept routes with the route target 10 unless I have a local VRF that is using the route target 10. So it's an automatic optimization of what routes you're going to accept. Okay, you don't need to manually configure this filtering. Okay, this is the problem that is happening right now on the command line. Okay, we didn't assign a route target to the routes. So what's happening is router 3 and 6, they actually are advertising the routes to each other, but they're not going to accept them. They're not going to accept them because they don't have the route targets configured locally in the VRFs. Okay, so this behavior is going to be on by default. We can disable this if we say no BGP default route target filter, and we're going to look at some situations where we need to do this because VPN routes may be transiting routers that do not have the VRF locally assigned. Okay, this is typically a case with inter-AS MPLS VPNs, where we have maybe a route reflector that is accepting updates from everybody inside the autonomous system, then passing them on to other autonomous systems. That route reflector may not be having any customer-facing interfaces. It could be used just to exchange BGP updates. So that's going to be a case we'll see when we go through that example that we would need to disable this route target filtering, which is going to be automatic. Okay, now, since the route target is a BGP extended community attribute, there's not an effective limit on how many route targets that a particular route can have. So when we set the route target on a prefix, we can set more than one. Okay, this is going to allow us to have some complex topologies to control what routes go between what VPNs. Okay, so at this point, what we're going to do is just choose the same route target on router 3 and router 6, so they both exchange the updates between those VPNs. So let's go ahead and look back at the command line here. so on router 3, under our VRF, we'll say IPVRF VPN-A. We want to define the route target. Okay, there's a couple different ways that we can do this. We can define different export and import route targets, or we can say when we're taking routes from the VRF and moving them into BGP, that's going to be our export route target. Set it the same value as when they're coming from BGP going into the VRF table. That is going to be our import route target. Okay, so we're exporting it from the VRF into BGP, importing it from BGP into the VRF. Okay, so in this case, we'll say for both of these, we'll use whatever arbitrary number that we define. It will say this is 100 for our BGP AS number. We'll say our AS is 1, and then this is VPN instance 1 inside our autonomous system. Okay, so this numbering scheme is going to be based on whatever administrative policy that the service provider defines. Okay, on router 6, we'll say the same thing. So IPVRF VPN-A, we want our route target to be 100:1. Okay, so there's a question here. So the route targets essentially allow us to connect the VRFs together, correct? Okay, the route target is determining where the routes are being advertised to, or not necessarily advertised, where they're actually going to be installed. Okay, without defining the route target policy, the advertisements are not going to move from BGP into the VRF table. Okay, so the route distinguisher is making the route unique. The route target controls our filtering policy. So what routes are we going to take from BGP and actually install into our VRF table? Okay, now if we look at the show IP BGP output, let's say show IP BGP VPN all, VPN v4 all actually, and we'll look at our local loopback here, 10.1.6.6. Okay, it says that it's locally originated by us. The extended community that is tagged onto this is the route target 100:1. Okay, that's what we define as our route target policy. If we look at the running configuration, what we can see is that when we advertise or when we activate the VPN v4 address family, it is automatically going to say that we need to send extended BGP community attributes between these neighbors. Okay, the route targets are encoded as BGP extended communities, so it is implied that this is a requirement of VPN v4 exchange. Okay, I'm not sure, as far as I have seen in all the versions that I've used this in, it does do it automatically, but keep in mind that this is a requirement. It could be possible that you have a version that doesn't do this automatically, so you need to send at least the extended community. Okay, if you want to do regular community manipulation, things like no export, local AS, no advertise, you would have to send both extended and standard. Okay, so you would say for this neighbor, send community both. Okay, so if we look at the VRF table now, or the VPN table I should say, show IP BGP VPN v4 all, we see we have the routes that are from us locally from router 6. Let's take a look at this on router 3 as well. Show IP BGP VPN v4 all. Okay, now they're starting to get updated. Okay, we can see that there's actually two different tables we have here. Two different, and they're based on the route distinguisher. Okay, we have routes that are coming from router 6 with 150.1.6.6:1. These routes, if we say show IP BGP VPN for the specific route distinguisher 150.1.6.6:1, look at the route 10.1.6.6. Okay, this is saying show us the information for this specific prefix. Okay, we can see that this has a route target of 100:1. It has a route distinguisher of 150.1.6.6:1. This is the actual route. Okay, these two together, these two fields, the route distinguisher and the route, this makes up the VPN v4 prefix. Okay, so we're receiving the prefix. We see the route target is 100:1. So now router 3 locally, it says, look at our VRFs and see if anyone is importing 100:1. And in VRF VPN-A, since we said route target both, it's both export and import, we are importing 100:1. So it says we received a route with the target 100:1. We have VRF VPN-A, which has that import policy. So now we are going to install it in that VRF table. So on router 3 now, if we say show IP route VRF VPN-A, we should see that route installed, which we do. And now if we go over to router 7 and we say show IP route, we see that router 3 had those routes via BGP. It was redistributing them into IGP. Now router 7 has them as IGP routes. They're learned via RIP. Okay, so what we should be able to do here is we'll ping 212.18.0.1, and we're going to source it from 10.1.7.7. Okay, so we can see that we have the route installed. We have it via IGP. We know the correct outgoing interface. The outgoing interface is Fast Ethernet 03 towards router 6, but right now we don't have transport for the prefix. Okay, let's go ahead. Let's go on to backbone 1, and let's make sure that backbone 1 has the route back to us. Okay, right now backbone 1 only has a route to router 6. So there's something going on in router 6. It's not taking those routes and advertising them into the PECE protocol. So let's take a look back on router 6. We'll say show IP route VRF VPN-A. We have the routes from RIP, but we don't have the routes from BGP yet. Okay, so let's look at the VRF table for the BGP VRF table for VPN-A, and then see if those are being learned from router 3. So we'll say show IP BGP VPN v4 all. Okay, so look at every single VPN v4 route we have in BGP. Okay, so right now we can see that we're not learning anything from router 3. Okay, next thing we need to look at the routes that router 3 is exporting into BGP. Do we have a matching import route target configured? Because router 3 is taking them from IGP, exporting them into BGP, and setting the route target based on the export route target. When router 6 receives this, it looks in the local configuration. It says, do I have a VRF that has this route target as an import route target? So I want to import it from BGP into the VRF. So let's say show run include import. Okay, we do have that import route target. Now, in addition to, let's go over to router 3. Let's make sure that it is actually tagging the route with that route target. We'll say, for example, show IP BGP VPN v4 all, and let's look at the route that is coming from router 7. We'll say 10.1.7.0. Actually, we may not be able to see the route target locally here. Let's take a look at the running configuration. Okay, so we are exporting them here with 100:1. So at this point, it looks like our configuration is right. What I'm going to do is clear the BGP relationship between them and try to force the update. Okay, so on router 3, we'll say clear IP BGP VPN v4 unicast in AS100. We'll say outbound to router 6. Okay, the syntax can get kind of complicated here when we're dealing with this. So use the context-sensitive help. It's going to be your friend with a lot of these complex show and clear commands for BGP. So now we sent a triggered update out to router 6. Let's see if router 6 received it now. Okay, so on router 6, let's say show IP BGP VPN v4 all. Okay, it's still not receiving them. So we tried doing a route refresh. Let's try route refresh inbound on router 6. Okay, another way to see if we're actually receiving these, we'll say show IP BGP VPN all summary. Show not clear. Show IP BGP VPN v4 all summary. Okay, so it says that we're not even receiving any prefixes from router 6 or from router 3. Okay, so at this point, after clearing it, we tried to do a route refresh. It wasn't working. So what I'm going to do is just clear. We'll do a hard clear of the BGP process. We'll just say clear IP BGP 151.3.3. So we'll drop the TCP session, and we'll try to get these neighbors to reset. Okay, so we're still not receiving them from router 3. Let's check. Let's make sure that router 3 is doing the redistribution process correctly. Show run, begin router BGP. Okay, we are redistributing RIP in there. Let's try clearing it. We'll say clear IP BGP asterisk on both of them. Sometimes you'll see that this stuff is slow to converge. Okay, let's go ahead and take about a 10-minute break. I'm going to try to troubleshoot this configuration real quick. We'll start back in about 10 minutes, and then we'll continue with the verification process here. So let's take a look back at the command line here. The problem that we were running into, we disabled on router 6, when we configured the BGP peering over to router 3, we disabled the negotiation of the IPv4 address family. Okay, we did that by going under the IPv4 unicast and saying, for this neighbor, we do not want to activate them for this address family. Okay, router 3 we saw previously, we left its default configuration on there for IP version 4, and when we looked to show IP BGP summary, it said that that was not negotiated. Okay, so the problem was we had to disable the negotiation of IPv4 on router 3 because the neighbors, in order for them to properly exchange updates, they need to be supporting the same capabilities. Okay, so if you're not running IPv4, then you need to disable it on both ends, assuming that you are disabling it. You can just leave it on there by default if you want to, if there's no requirement, but in this case, we are specifically disabling it. Okay, so now if we look at the show IP-BGP VPN v4 all summary output, we can see that router 6 is learning prefixes from router 3. It is learning 3 prefixes through VPN. Okay, if we look at the show IP-BGP VPN v4 all output, we can see routes are being received with the route distinguisher 150.1.3.3:1, and we have them installed in the VPN v4 table. Now we can see that these prefixes are actually listed twice. They're listed under router 3's route distinguisher, and they are listed under router 6's route distinguisher. Okay, the reason why is when they are imported into the VRF table, router 6 is importing it with its own route distinguisher. So we can see the loopback of router 3, it's being imported. The next hop is staying the same. The next hop is 150.1.3.3, but router 6 is using its own route distinguisher. Okay, so if router 6 were to turn around and advertise this to another neighbor, we would see that it would be advertising it with its own route distinguisher instead of router 3's distinguisher. Okay, so if we take a look at backbone 1 now, if we look at the show IP route RIP output, we see backbone 1 is learning the routes from the other customer edge router, which is router 7. Okay, so we should be able to go over to router 7 now and have reachability to backbone 1, which we do. Okay, now what we should note here, let's take a look back at the diagram. Is that in the transit path on router 1 and router 5, they're not running BGP, and they do not know about the routes that are coming either from router 7 or from backbone 1. Okay, so router 6 is receiving routes from RIP, in from backbone 1. It's redistributing RIP into BGP and advertising them as VPN v4 routes over to router 3. Router 3 is then taking the VPN v4 routes, importing them into the VRF table, and advertising them as RIP routes out to router 7. Okay, so we're performing mutual redistribution between RIP and BGP on both router 6 and router 3. And now, again, if we look at the logic of how the VPN forwarding is going to work, the MPLS VPN forwarding, router 6 is advertising, in addition to the regular prefix, is advertising a VPN label. So router 6 is saying to router 3, in order to get to those routes coming from backbone 1, you're going to use me as the next hop, and you're going to use the MPLS label that I am advertising to you. Previously, what happened is that router 3 already knew an MPLS label, a transport MPLS